For this question here, we're considering which of these molecules are nonpolar. So the nonpolar molecules are going to be the one who have their dipole moments cancel out. So we have to consider their molecular geometries. So we're going to have a bent bond in the case of SF2. You got to make sure to do and come up with the proper Lewis structure. We're going to have a central sulfur, 2 fluorines. Might look linear here, but it's going to be tetrahedral in shape, going to be a bent bond, closer to 109.5 degrees, definitely going to be polar. So that's not nonpolar. SF4, 34 electrons coming from 6 plus 28. Central sulfur, 4 fluorines, lone pair on sulfur. Each of the fluorines would have a lone pair around them. And you can see the fluorines aren't all opposing each other. We have this lone pair here. We got a net dipole moment bisecting the bent SF-S bond. So we definitely have a polar molecule. SF6 is going to be nonpolar because we're going to have an octahedral molecule. Why? Well, we have 6 plus 42 for 48 electrons, 48 valence electrons. We have a central sulfur, 4 fluorines. So the structure is going to take an octahedral geometry. All the bonds are opposing each other. Each of these fluorines are on an axis, so each of these individual dipoles here are canceling each other out. Bond angle is perfectly 90 degrees in this molecule, perfectly octahedral. PF3 is going to be trigonal pyramidal, like NF3 or NH3, so it's going to be polar. And then PF5 is going to be nonpolar, because we're going to have a trigonal bipyramidal molecule, 40 electrons. Central phosphorus, 2 fluorines on an axis together, 3 fluorines on an equator. So trigonal bipyramidal. All the fluorines canceling each other out for a nonpolar molecule. So what we want here is we want a molecule that's linear with 2 atoms in both spots. We want a trigonal planar with the same atom in both spots. We want tetrahedral, same atom across a molecule, trigonal planar. We want octahedral, or we want linear within the trigonal bipyramidal. So we also have trigonal bipyramidal. Oh, I said bipyramidal, I wrote planar. So trigonal bipyramidal, octahedral, square planar would also be nonpolar. So you just have to look at the bonds, see if they're opposing each other. If the dipoles cancel out, you have a nonpolar molecule, despite having polar bonds. So it looks like our answer is going to be 3 and 5. How many double and triple bonds does the molecule contain? CH2CH, CCH. So I put this together, just attach the hydrogens to the carbons that are indicated. And then from there, try to give each carbon 4 bonds. And so we have 4 bonds for this carbon, so that's good. We also have 4 bonds for the second carbon, so that's good. The last carbon and the last 2 carbons are deficient of bonds. They only have 2 bonds each right now, so let's go with a triple bond. Okay, so we're going to have 1 double, 1 triple bond. We can do a double check too. We got 1, 2, 3, 4 carbons, so that's 4 times 4, 16 electrons from the carbons, plus 2, 3, 4 for the hydrogens, 20 total electrons, and we can count those up. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So it checks out. For this question here, we're considering the hybridization of each molecule. And so we're looking for sp3 hybridization. This means we're looking for tetrahedral. We're looking for something that has a tetrahedral domain. CO2 is going to be linear. PCl5 is going to be trigonal bipyramidal. CCl4 is going to be tetrahedral, so we're going to have 4 chlorines. I didn't mean to draw that one coming out at us. So just this one's coming out at us, this one's going back. And then each of the chlorines has a lone pair around them. That's 8 around each. That's 32 electrons, which is the total we have for the molecule, so that's good. So CCl4 is tetrahedral. BCl2 is also linear, kind of like CO2 is. BCl3, trigonal planar, so just CCl4. For this question here, we're considering which has a greater bond angle. So we're looking at NH3, the HNH bond angle in NH3. So we have nitrogen lone pair, hydrogens. First, the bond angle in CH4. Now in CH4, we got perfect tetrahedral. We got bond angles of exactly 109.5 degrees the whole way around the molecule. In NH3, we're going to be slightly less than 109.5 degrees due to the lone pair bond pair repulsions pushing the bonding pair electrons closer together. So we're going to have a greater bond angle for CH4. Now pH3 is going to be like NH3, trigonal planar. It's like NH3, pH3 with central phosphorus, hydrogens, lone pair. So angle is going to be less than 109.5 degrees. The angles of BH3, trigonal planar now, only 6 electrons. So we're good trigonal planar, no electron pairs on boron. So these bond angles are exactly 120 degrees with no variation. So the bond angles in BH3 are definitely greater. And then the last one is looking at the double bond versus single bond repulsions in formaldehyde, C double bond O, hydrogens. This bond angle here is going to be less than 120 degrees, slightly greater than 120 for the double bond, single bond repulsions. So the bond angle is slightly greater for the HCO double bond O angle in CH2O. So we got NH3, BH3, and then the HCO angle. Sigma and pi bonds. And so the idea here is we could look at the hybridizations of each of the carbon atoms here. So all the carbons here are going to be sp hybridized. Why are they sp? Because they're all linear. So they should have an sp orbital pointing in each direction. The sp orbital overlaps with each other. And then the sp overlap with the hydrogen 1s give us sigma bonds. Nitrogen has a lone pair, so we get the sigma bond here. So we're going to have a total of 1, 2, 3, 4, 5, 6 sigma bonds. And the sigma bonds are from the overlapping, in the case of the adjacent carbon atoms, from the hybrid orbitals overlapping. And then in the case of the hydrogen, it's the 1s overlapping with the hybrid orbital. In the case of nitrogen, it's sp orbital overlapping with the carbon sp orbital. And so then the double and triple bonds, the other two bonds in the triple bond are made about from the p orbital overlapping orbitals. So we get the p orbitals overlap for one of the extra bonds and then sticking straight out. It's hard to picture these on the same axis together, but perhaps if we try a different color. So let me try green, perhaps. Green sticking out. Then we do it again here. Green sticking out, overlap, black in plane, overlapping for another, and then the same thing here. And so if we think of a triple bond as being a sigma plus the 2 pi bonds, so the C triple bond C or the C triple bond N bonds are described as being 1 sigma plus 2 pi. Pretty easy just to count up having 2, 4, 6 pi bonds. So 6 sigma, 6 pi. Next question, which one has the longest carbon-carbon bond? So we have CH3, CH3 for a single bond. We have the double bond for the next one. And then, of course, the triple bond for the last one. More electrons are going to bring the nuclei together. I think it's pretty easy to Understand that the electrons are negative particles. They're going to bring the positively charged nuclei together through having more shared electrons. So we get the shortest bond for C2H2, but we're looking for the longest bond. So the longest bond is going to be C2H6. So longest bond with only 2 electrons to share, shortest bond with 3. So this will be the weakest bond. If we're going to break it, this is the weakest bond. Also the longest bond. And the carbon-carbon triple bond here is going to be the strongest of these 3, and then the shortest. Okay, according to their molecular orbital diagrams, which molecule below is paramagnetic, hence will be drawn into a magnetic field. So the word paramagnetic just simply means that the atom contains one or more unpaired electron. And if you contrast that with diamagnetic, equals 0 unpaired electrons. And so if we're doing these diagrams here, let's start with, you got to make sure we use the right side. The diagrams, the idea is that these are the 2s orbitals and the 2p orbitals overlapping with each other. So we're considering the relative energies here of these interactions. We have the 2s and the 2p for O2, F2, neon 2. And so let's do C2 first. So if we have C2, we'd have a carbon atom on either side. We're really just trying to get the right count here. We're getting 4 valence electrons from each of the carbon atoms, and then we're simply having 8 in the middle. In the middle, we're depicting the C2 molecule. So on either side, it's like you have one carbon atom, the other carbon atom, and they're approaching each other. And then the idea is you get the S overlapping for bonding and anti-bonding. So you get your sigma 2s going down in energy, so your sigma orbital 2s because you get the sigma type bonding, sigma star for the anti-bonding contribution, and then you get the pi orbitals that are next for carbon. We'll talk about this in class on why the pi are next in energy, but the 2p orbitals can overlap. If you imagine one carbon atom and its positively charged nucleus has p orbitals that are overlapping this way, so we get pi overlap with the one, pi overlapping with the other, so we get a degenerate equal set of orbitals for our pi 2p. Then we get the pi star 2p going up in energy relative to where the 2p orbitals are. Then we get the sigma combination. The sigma combination are the p orbitals that are aligned pointing at each other, overlapping with each other, making a bonding and anti-bonding combination. So we get a sigma 2p here, the sigma type orbital because it's on the bond axis, and sigma star 2p going up in energy. So we just fill 2, 4, 6, 8 electrons in, all spin paired. So we get diamagnetic for C2. If we go to O2, go to N2, do 2 more electrons. So we're just going to throw 2 more electrons in here to do N2. We end up with 2 more electrons up here. For N2, we end up with it diamagnetic as well. And then if we go to O2, it's easier if you start with the one with fewer electrons first. So O2 would have 6 valence electrons each. So here we have 6 valence electrons for each of the O's coming together to form O2 in the middle. So we're just putting 12 electrons in the middle. So 2, 4, 6, 8, 10, and then 12. We apply Hund's rule, pair those electrons in the same direction. We end up with a paramagnetic molecule. And really this is the whole point of MO theory, is seeing that O2 comes out to be paramagnetic. If you're looking at the Lewis structure of O2, you see the Lewis structure, you would predict all these electrons look spin paired to me. The Lewis structure wouldn't predict that 2 of these electrons actually end up with their electrons paired in the same direction for a net spin on the molecule. As well, hybrid theory, valence bond theory wouldn't predict that we have unpaired electrons either. MO theory gets this right. So really this is why I think we're talking about MO theory here in this chapter, so we can better understand some of the properties of O2. And so F2 just would put 2 more electrons in. Let's use a different color. So for F2, we put 2 electrons more. So then we pair up the electrons. We have nowhere else to put them other than pairing their spins up, and it goes back to having a spin of 0, diamagnetic, not drawn into a magnetic field. So only O2 of these molecules is paramagnetic. Okay, now we can rank molecules using bond order here.
So this one's going to look at O2, B2, and N2. So let's do B2 first. So B2 would have a boron atom, 2s2, 2p1, 3 valence electrons, another boron with the same number. What we write here is somewhat inconsequential because what we're really trying to understand is what happens when the two boron atoms overlap with each other. And the answer is we're going to fill 6 electrons in. 2, 4, 6 electrons. How do I know to fill 6 in? Well, each boron has 3 valence electrons, so that's where I get the 6 electrons from. And then the orbital energies, we got a sigma 2s, again, a sigma star 2s. If you see any orbital that goes up from the atomic orbitals that it's constructed by, that's a star. That's an antibonding orbital. Then we get a pi 2p, and then it would go sigma, but we don't have any electrons there, so let's not worry about them. And so our bond order is going to be equal to 1/2 times the bonding number of electrons, which those are going to be these 4 electrons here, or our bonding electrons. And then we're going to subtract the anti-bonding electrons, which are going to be these ones here. Those are anti-bonding electrons. So bonding electrons bring the nuclei together. Anti-bonding electrons sort of do the opposite. They take the nuclei apart, and they sort of break the bonds we're trying to make through the bonding electrons. And so our net bond here is just going to be equal to 1/2 times 2, or 1. 1 is a single bond. So this means B2 probably looks like this. 2 borons with a lone pair on each. And probably not best described with a triple bond. A triple bond is what we would predict if you had a bond order of 3 or a bond order of 1. We get a bond order of 1, which supports having a single bond in the Lewis structure. Do the same thing for O2. Let's do O2 next, and we'll do N2. So we have oxygen. So we're going to have 2 times 6. So we're going to go sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, sigma star 2p. You know the pi's are the pi's because there's 2 of them. You know the sigmas are the sigma because there's 1 of them. And you get 2 of the pi's when you're like this, because you get these 2 sets of orbitals that are exactly the same as each other. So you get 2 orbitals that are degenerate in the pi bonding case and the planar bonding. So if we just fill our 12 electrons in, 2, 4, 6, 8, 10, 12. We did this one on the previous slide too. But 2 unpaired electrons, paramagnetic, but our bond order, our bonding electrons are going to be these 2 and then these 6. Then the anti-bonding electrons are going to be these 2 and those 2. So we're going to have 8, and the most bonding electrons you can have is 8. The most antibonding you can have is 8 as well. But then we only have 4 antibonding multiplied by 1/2. So our bond order is going to be equal to 2. So our bond order is equal to 2, means that you would have oxygen-oxygen double bond in terms of a Lewis structure. And then we're going to have, maybe something like this where you're just picturing spin-paired electrons and then spin-paired in the same direction. And you don't have to worry too much about this Lewis structure, but it's maybe one where we get, a Lewis structure where we have some unpaired electrons being shown is maybe the point to match up with the predicted diagram, the molecular orbital diagram. Last one we need to do is N2. N2 just has 2 more electrons for each N. So for N2, we have 10 electrons total on the molecule, 5 times 2. So we add 2 more. So we had 6 for B2, now we need 10. So we just simply spin pair, and the last 2 electrons go in. And you can, clean off the diagram, start fresh, and we could do that to kind of show that the idea here would be just going from 2, 4, 6, 8, 10 electrons in, just in order of high to low, but following Hund's rule for degenerate orbitals. And so then we get 10 electrons going in. And then the bond order, we only have these 2 anti-bonding electrons, and then we have these bonding electrons. So 8 bonding, 2 anti-bonding times 1/2 is equal to 3. So that's a triple bond. So N2 ends up looking triple like we expect. So a triple bond, all electrons spin paired. Our ordinary Lewis structure looks pretty good for N2. So most structures that we've learned so far, we reinforce what we already know about them. O2, we get a little bit of a refined answer and a better prediction of its magnetic property. But in terms of the bond length, our triple bond is going to be the shortest. Our double is going to be next. So whenever we're comparing atoms in the same row of the periodic table, we can just make light of the fact that single bonds should be longer than double, longer than triple. So we're going to go B2 as the longest, then O2, then N2. So we're just going to rank an order single, less than double, less than triple. So just rank these sort of with the order. That's actually the opposite order. The order would be single, longer than double, longer than triple in terms of length, and obviously the opposite trend in terms of bond strength. Last question, which MO diagram or like which Lewis structure is most consistent with C2? So for carbon, we're going to use the proper diagram for carbon. C2 would be 2s, 2p2. We should put 8 electrons in, 4 for each carbon. And so we're going to put 4 in for C2, 2, 4, 6, 8 electrons. So our bond order is going to be equal to a half times 8, not 8, a half times, we got 6 bonding electrons. Let's circle them again or highlight. Let's highlight them. So we got, these are the bonding electrons. So that's 6. And then these are the anti-bonding electrons, 2. So a half times 6 minus 2 is equal to 2. So we have a double bond between 2 carbons. So double bond, and then all the electrons are spin paired. So I would go with this structure here. It looks pretty good for C2. And so this is a little bit of a different structure. Like by using the ordinary rule that we have for diatomic molecules that they should satisfy the octet rule, you might look at a structure like this. But according to MO theory, we're never going to get a quadruple bond because of these anti-bonding electrons in the way. So the most we're ever going to get, according to MO theory, is a triple bond for atoms in the second row of the periodic table. So we end up with a double bond being consistent with the bond order as the best Lewis structure for C2. Okay, so that's all of this activity. Hope this helps. You guys run your recitations this week. Have a good week. Take care.